Hello students. So today we will start with Introduction to Automata Theory. This is under your Module 1 of your syllabus, that is regular languages. So we will see what is the history lying behind this automata theory. Right. In 1930s, a scientist named A. Turing studied an abstract machine that had all the capabilities of today's computers. So it is really a stunning feature that in the era of 1930, so here the Turing has come to build a machine that can perform all the functions which a computer can do, right? Then Turing's goal was to describe precisely the boundary between what a computing machine could do and what it could not do. So what are the restrictions of a computing machine? What it can do? What it cannot do? What are the restrictions? What are the drawbacks? All everything was defined there. Right. Next, in 1940s and 50s, simpler kinds of machines, which we call today finite automata, were studied by a number of researchers. So in this course, we will see what is a finite automata. We will see different classifications of finite automata, and we will later after studying all these things, we will move to means how automata act, and how can automata help to design a compiler, and so on. That is the main motive of this paper, right? And this automata, originally proposed to model brain function, turned out to be extremely useful for a variety of other purposes. So we will see everything one by one. So in 1940s and 50s, this finite automata was firstly proposed. Now, in the late 1950s, Chomsky, a scientist named Chomsky, began the study of formal grammars. We will see this, what grammars are. We will see how to represent different kinds of automata, what are the restrictions of finite automata, how it can be enlarged, and how to depict what languages it can accept. We will see everything one by one, and the grammar is a very useful part of it. So Chomsky 1950, he firstly classified the different types of grammars which we will use later on. While not strictly machines, these grammars have close relationships to abstract automata and serve today as the basis of some important software components, including parts of compilers. So as I have already introduced beforehand, that the main motive of this syllabus is to gradually move towards the designing of compilers and all. So these grammars has a very useful impact in how the software components, how we can develop the software components which can be treated as compilers, and so on. Okay. Next, in 1969, Cook extended Turing's study of what could and what could not be computed. As we have seen that Turing only said that there are some parts which a computing machine can perform, and there are some parts which a computing machine cannot perform. Now, Cook has extended this, and he clearly distinguished what task or what job a computing machine can perform and what jobs that computing machine cannot perform, right? And then Cook was able to separate those problems that can be solved efficiently by a computer from those problems that cannot be solved. Principle means the principle behind that, we have to conclude that these problems are not solvable, right? So we will see in the in latter part of our syllabus, or you can say at the end of our of this syllabus, particular class of problem which we called NP hard problem. Okay, we will see those in our later classes. Now this is most important part. What is automata, right? So the term automata is actually a Greek word which is written in Greek language in this format you can see in the presentation, which means self-acting. Means automata is such a kind of machine which can self-act, means it can receive some input, process it, and give some output, right? And automaton is the singular form of the term automata, right? It is an abstract self-propelled computing device which follows a predetermined sequence of operations automatically, right? So predetermined means as our study progress we will see that what predetermined is. It can accept a set of inputs it can process and can act accordingly. Predetermined means it has been previously programmed that with this set of inputs it will process and will generate this kind of output, right? So this is a very simplest example of automata, or you can say finite automata. This is a switch, right? So as we progress, we will see there will be some states. We can move from one state to another. We can give some output and can receive some, we can give some input and can receive some output. So here we are having two states. One is called off, another is called on. So we will see the states will be encircled within a circle. So here off is the start state, means we are starting our job from the off state and we are applying one action named push. So if we push the switch, it will move to on state, and again if we again push the switch, it will come back to the off state, right? So this is one on off finite automaton switch, very easy to understand. So we are starting with off state, and after applying push we are moving to on state, and again after applying push we are coming to off state, right? So here no one is marked with a single arrow named start. So in our study we will depict this stage as a initial stage, and here no final state is mentioned. You can say if our motive is to move to on state, then on will be the final state, and again if we think that we have to come back to our off state, then off will be the final state. We'll see how to depict this on and starting and final state. Next we will see a formal definition of finite automata. Here a finite automata, we have already learned that automata is a self-acting machine. So it will be depicted with a 5 tuple, means in if we develop a mathematical model, we will say it's a 5 tuple structure. What are those? First is q, then it is capital sigma, then small delta, then q naught and capital F. What are these things? As we have seen in our previous diagram, that to design a finite automata we need some states, we need some actions, we need one final state, we need some initial state, and so on. So here capital Q is a finite set of states, means since this is our finite automata, so our number of states should be restricted, or it has to be finite, right? So Q will contain all the states that are present in that finite automata, and then sigma is a set of symbols called the alphabets of the automaton. So if we move to our previous diagram, so here you can see that what are the inputs present. One is push, another is similarly push. So sigma will contain push only, q will contain off and on, right? So here again so here we have defined q is a set of states, it is on and off, and sigma here if we compare to that diagram, it is only the input states, that is push, right? Now delta is the transition function. What is transition function? Transition means if we apply input to a particular state, it will move to another state. So what can be the transition? If we combine a state with the input, that can be the transition function. So it will ultimately generate another state, right? Q naught is the initial state from where any input is processed. It is obviously a part of our capital Q. So in that diagram we have seen that there off was the initial state, and F is a set of final state. F can be one state, or F can be more than one state. So there can be more than one final states in a finite automata, right? Next we will learn some terminologies associated to this. We have seen already that sigma is called alphabet, right? An alphabet is any finite set of symbols. It can be A, B, C, D, it can be 0, 1, 2, anything, right? Then string. String is what? With this set of alphabets, say here with A, B, C, D, what are the strings that we can form by combining all this, okay? So an example can be C, A, B, C, A, D. Anything can be, any combination of A, B, C, D, any possible combinations. Next, length of string. Length of string means how many characters are present in a particular string. So if we consider our previous example CABCAD, the length will be 6. Right? There can be empty string also, means there are no characters present in a particular string, then obviously that length of that string will be 0. Right? Now one very interesting concept is there called clean star. What is this? This clean star is the what can be the combinations, or what means what can be the various combinations of string including the null string, right? So if we consider our sigma to be AB, means it consists of say two symbols, one is A, another is B. So what can be the clean star? It can be null, so it is depicted by lambda. It can be of single length, means it can be A or it can be B. It can be of double length, means AB, BA, BB. And so if we proceed like this, it can be of any length, right? It can be an infinite set of all the combinations of AB. Next is another thing present, clean closure or plus. It is very similar to the previous one, clean star, except one exception is there. It will not consist of the null string, means it can here the string cannot be of zero length, right? It can be of single length, double length, triple length, and so on. Now what is language? Language means, say we have seen that after the combination of the different symbols we can generate different strings, right? Like AB, AA, BB, AB, anything. So if we restrict our language to a feature such that the length of the language is 2, right? So we will only consider the combinations of AB where the length is 2. So this can be a language of the finite automata. Fine. So this is the end of our first class. Next class we will see one important uh, type of automata called deterministic finite automata. Thank you.